We're good. Okay, guys. All right. Let's go over what these equations mean. We're going to be talking about transformers and current and voltage generated when the flux changes. First thing, transformers, if you remember from the notes when we did it, it's something that either steps up or steps down voltage. So the voltage going in will be 120 volts. If it steps it up, it can step it up really to anything but 10,000 volts or something like that. Then a step down and take it from 10,000 back down to 120. So what they're usually used for is to change voltage to transmit it. Because less power and energy is lost when you transmit electricity at high voltages. So what they usually do at the power company, they'll have step-up transformers to step up the voltage from 240 to maybe 10,000, kind of making up those numbers. But they'll step it up because it's much easier to transmit energy at high voltage because it loses less energy. Then when it gets to your house, by the time it gets to your house, they've stepped it back down to about 120. Because if they didn't step it down from 10,000 volts, when you walk by your outlets, they would shock you, essentially. Probably electrocute you, but it would be unpleasant. So we'll leave it at that.
So if one of those went out, the transformer steps it back down?
If the transformer, a lot of times that's what causes power outages, the transformer will blow.
Yeah.
So a squirrel will touch the power line to the transformer, and the transformer then gets shorted out, so it doesn't work anymore. So if it shorts out, you lose power. It doesn't the voltage doesn't stay up. Does that make sense?
It's part of the plumber.
All right. So the equation here, transformers is two loops, or two coils of loops, and N is the number of coils. So N sub S is the number of coils in the secondary loop. That's the one that's going to be outputting the voltage. And N sub P is the number of coils on the primary one. So it's usually referred to as coils or turns. So the primary one is the one that's receiving the voltage, so it goes into the primary, out the secondary. Wait.
Got it.
And then V sub S is the voltage on the secondary one. V sub P is the voltage on the primary one again. So usually you're going to have three of those things and be solving for a fourth. Okay. Next equation is for magnetic flux. And that, you see that Greek letter, it's Greek letter phi, it looks like an I with a circle in it. That's the magnetic flux. And that's measured in something called Webers, WB. And then B is the magnetic field, and A is the area. There's also a, it's not going to come into play in this class very much, but there's a cosine theta in there as well. You'll probably see that in college at some point if you take a physics class. Alright. And that flux is going to be used to calculate the voltage if the flux is changing. So next equation is voltage. You'll also see it referred to as EMF. If you see EMF, that means voltage, and kind of the same rule as last chapter. If it's something you don't know what it is, it's probably voltage. And voltage is created by changing flux. So the voltage equals negative N, which is the number of loops or number of turns again. And then it's the change in flux. So it's going to be the change in B times A divided by the time. And the time is going to be in seconds. Any questions on that?
What was the N again?
N is number of turns. So N is always the number of something in every equation. Okay. Next equation involves AC current, just like the current we get out of the wall outlet. So we have voltage and time here. When you have an AC circuit, the voltage kind of goes like this. It alternates between high and low voltage. The max voltage would be the highest the voltage ever gets. But because it's going between two values, it's not the most useful voltage. Does that make sense? So the voltage you actually use is going to be somewhere in the middle of that. So the voltage that's usable, we call it the root mean square voltage, and it's referred to as V sub RMS. So that's what that equation is for. So the useful voltage VRMS is equal to 0.707 times the maximum voltage. Anybody know where that .707 comes from? Not James Bond. That'd be 007.
Probably some math equation.
It's the square root of something over something.
Square root of 3 over 2.
Square root of 2 over 2.
Close.
Okay. So that equation will come up periodically. A lot of times it'll be asking you to find, like, with the transformer equation, you'll find the RMS voltage, and then it'll ask you to find the maximum voltage produced. And also remember that V equals IR, that'll come into play on some of these as well. Any questions about what those equations stand for or mean? Okay, let's do number 1 together. Number 1, a step-down transformer has 2,400 turns on the primary and 190 turns in the secondary. If the RMS EMF, so RMS voltage across the secondary coil is 120 volts, what is the maximum EMF or voltage across the primary coil? So what we're going to do is we're going to use the transformer equation to find the RMS voltage, and then use that VRMS equation to find the maximum voltage. Okay, so first equation we use N sub S over N sub P equals V sub S over V sub P. Alright, what is the number of turns in our secondary coil? 190 over primary coil?
2400.
2400. I'll go like this percent.
No,
You
you
have
don't.
to.
No.
This guy's
You're
annoying.
doing something?
Yes, I'm teaching.
Oh, he's actually.
I say.
Okay. What is the voltage in the secondary coil?
Yeah, it's
120 volts.
Get out.
120 volts.
120 volts, thank you.
That's the kid who thought this
It's
guy was
big.
going.
Alright, and then we're going to solve for the voltage in the primary coil. So cross multiply and divide, so 2400 times 120 divided by 190.
515.79.
So 1,516 volts. One thing, since it's a step-down transformer, when it says step down, that means your primary should be larger than the secondary. Does that make sense, everybody? Alright. Next we're going to use VRMS equals 0.707 times Vmax. So we've got 1516 equals 0.707 times Vmax. So the maximum voltage in the AC circuit is equal to 1516 divided by 0.707, and what does that equal?
2,144.
270. And that's volts. So if they ask you to find the current, then you just use V equals IR, but you'd have to have a resistance then. So that's the only other thing I could really do with something like this. Any questions about this one? Erase it. The math in this section is really not that hard. I mean, this is as hard as it kind of gets.
Really?
The hardest part of this section is the right-hand stuff. I mean, there are a decent number of equations you got to keep track of, but it's really still not that many. All right. Number 2, a coil with, well, it ends up being 951 turns and a cross-sectional area of 1.23 meters experiences a magnetic field for for 2.75 seconds. The plane of the coil is perpendicular to the plane of the magnetic field. If the magnetic field changes from 0.389 teslas to negative 0.329 teslas, what's the induced EMF in the coil? All right. So what equation are we going to use to find this one? Since we have
V equals negative N.
If so, V equals negative N is the change in flux over T. Alright, let's plug stuff in there. What is the number of turns?
151.
Alright, so now we need to do area times magnetic field for both, and we're going to do final minus initial. Okay, so what's the area?
1.23 meters squared.
And what is the initial magnetic field?
0.389.
Is it? Sorry, what is the final magnetic field? It's final minus initial.
329.
We have 0.329 Teslas. Put it right bigger here, don't we? And then minus the initial, so it's 1.23 meters squared times, what's the final, or the initial now?
0.329.
Great.
0.389.
9 Teslas. And how long does it take for the magnetic field to change? 2.75 seconds. Not entirely clear in the problem, but that's what it means. So what is our induced voltage?
.41.
So let's say 305 volts for the induced voltage. Any questions on that? Okay, erase this one. Alright, we'll do one more together. You guys can do the rest on your own. Alright. A 5.49 centimeter square coil of wire. So this is like a coil of wire that's wrapped up in a square. And when it says 5.49 centimeters, that's the length of one side. Does that make sense? With 130 loops is pulled from a magnetic field of 0.69 Teslas. It takes 0.181 seconds for the coil to be removed from the magnetic field, and the resistance of the coil of wire is 145 ohms. What is the current created in the loop? So same equation. But what we're going to have to do at the end since it asks for current.
V equals IR.
V equals IR. Start off with negative. How many loops are there?
130.
130 times, what is the final flux in this case? What's the final area? One of the important things about flux is that the area is the area that's in a magnetic field. 0. So our final flux is 0 because it's removed from the magnetic field, so there's no magnetic field lines going through the wire. Going through the loop. So we end up with 0 minus, what's our initial area going to be? Do that over here.
5.49 centimeters. Nope, that's not.
Okay, so we got to convert from centimeters to meters, so we divide by 100. So our area is going to be 0.0549 meters squared. And what's our area end up equaling?
Wait, so it's just centimeters, it's not centimeters squared, so you get that.
Yeah, so we got to convert it from centimeters to meters, and then square it to get the area. So it's 0.0030 meters squared. So that's our area. And then what is the magnetic field through it? What is it?
0.181 seconds.
The area.
Sorry.
So what's the area? I can look it up.
It's the magnetic field, right?
Oh yeah, sorry, the magnetic field.
0.69.
0.69 Teslas. And like Ryan said, it is 0.181 seconds. 1.48.
1.49.
Okay. So now we just use V equals IR to find our current. So we get 1.49 volts equals I. And what's our resistance?
145.
145 ohms. And what is our current equal?
0.01.
It ends up being a very small current in this case. Okay. Anybody have any questions over these? Again, there's not too much with this. What we're going to do tomorrow is probably going to be slightly more confusing, but it's still, the math of this section is really not that bad compared to some of the other stuff we've done. No questions? When you guys finish this, I have the answers up here. I'll come around and help you as needed.